Hello all. In my previous class, I discussed compensated semiconductor, right? And also calculation of the extrinsic Fermi level with respect to intrinsic Fermi level. Nothing but Fermi level of doped sample with respect to undoped sample. Now in this class, I will start with temperature effect on mobility in a semiconductor. Already we discussed temperature effect on mobility in a conductor or a metal in our first chapter, that is classification of the materials, right? The same way, temperature effect on mobility in a semiconductor. See, in a semiconductor, the mobility is affected due to temperature in two ways. One is lattice scattering, and another one is impurity scattering. Impurity scattering. Right. So first I start with lattice scattering. What is lattice scattering? See here, in case of semiconductor, as temperature is increased, what about the thermal energy supplied to the semiconductor? Thermal energy supplied to a semiconductor is increases. If thermal energy supplied to a semiconductor is increases, means what about the vibrations in a lattice actually increases? Vibrations in a lattice is increases. If vibrations in a lattice increases, means what about number of collisions actually? Number of collisions also increases. Number of collisions increases means what about the mean time actually? The mean time is decreases. Here, number of collisions and mean time both will be inversely proportional, right? If mean time decreases means what about the mobility actually? The mobility also decreases, right? Here, mobility is decreased due to increasing of vibrations in a lattice is called as what actually? Lattice scattering. See now, see, due to lattice scattering, as temperature is increased, what about the mobility? The mobility is decreased because of lattice scattering. And one more point actually, here how the temperature and mobility is related actually, both will be inversely proportional, that is mu proportional to T power minus T by 2. This is the relation between mobility and temperature. And also this lattice scattering is considered very high temperature. And very important point, this is considered very high temperature actually, right? Right on. Write on the notes. In a semiconductor, mobility is affected due to temperature in two ways. The first one, lattice scattering. And second one, impurity scattering. Yeah. Again, heading lattice scattering. Right. Copy this one, copy this flow graph, and copy this relation. Copied? Right. Right on this point. Lattice scattering is considered very high temperature. Yeah. Underline very high temperature. Yeah. Next heading, impurity scattering. Right. So now See, this impurity scattering is considered at low temperature actually. This impurity scattering is considered at low temperature. See, at very low temperature, all charge carriers having low energy levels, right? So charge carriers means, for example, if we consider a p-type semiconductor, if p-type content I want actually, it contain acceptor ion along with hole, acceptor ion along with hole, right? Here the charge carriers are holes. What I'm saying here, this impurity scattering is considered at very low temperature. At very low temperature, all charge carriers having low energy levels. See, such a charge carriers are passing through a semiconductor. Such a charge carriers means here holes. Here, such a charge carriers are passing through a semiconductor. What happen actually? These charge carriers are offers a attractive force due to the impurity ions, right? Here hole having positive charge, acceptor having negative charge. That means what type of force in between? Attractive force. Due to this attractive force, the movement of the charge carrier further be decreased. Already the movement is decreased because of low energy levels. Again, because of attractive force, the movement further be decreases. If the movement of the charge carrier is further be decreases, then what about the mobility decreased? Right? Now here, see the flow graph of impurity scattering. Now here, as temperature is decreased, because here it is considered low temperature, right? So consider at low temperature means we can consider as temperature is decreased. As temperature is decreased, what about the impurity concentration effect? Impurity concentration effect. Impurity concentration effect is increased. Impurity concentration effect is increased means attractive force between hole and acceptor here. If impurity concentration effect is increased means what about the movement of the charge carrier actually decreased? If the movement of the charge carrier is decreases means what about the mobility actually decreased? That means what is impurity scattering here? Impurity scattering is nothing but here the mobility is decreased due to impurity concentration effect. It's called as impurity scattering. And also in case of impurity scattering, what you can observe actually as temperature is decreased, mobility is decreased. That means how temperature and mobility are related actually, both will be directly proportional. That means we have a relation that is mu proportional to t power 3 by 2. See, in case of lattice scattering, this is mu proportional to t power minus 3 by 2. Whereas in impurity scattering, actually mu proportional to t power 3 by 2. That means what we can understand in both lattice scattering and impurity scattering, as temperature is increased or decreased, what about the mobility actually decreased? Mobility is decreased, right? Now here I'm going to draw the graph between mobility versus temperature, that is log mu versus log t, right? See, in case of semiconductor, the two scatterings will be occur actually. One is lattice scattering, right? And another one is impurity scattering. See, due to lattice scattering, as temperature is increased, what about the mobility decreased? This is due to what actually? This is due to lattice scattering. And similarly, as temperature is decreased, then what about the mobility actually? The mobility is decreased due to what actually? Impurity scattering, right? Now this is the combined graph of mobility versus temperature in a semiconductor. See, that means what we can understand. See, if you increase the temperature up to room temperature actually, so the mobility will be increased. After that, the mobility will start decrease because of collisions. So this is the mobility versus temperature graph in case of semiconductor, right? Right on impurity scattering. It is considered, write in the notes, it is considered low temperature. It is considered low temperature, comma, at very low temperature, comma, at very low temperature, all charge carriers having low energy levels. Low energy levels. Such a charge carriers are passing through a semiconductor, then These charge carriers offers a attractive force due to impurity ions, right? Due to which movement of the charge carrier decreases. Right? Copy this flow graph and copy this equation. Right. Next, observation. Next heading, observation. In a semiconductor, temperature is increased or decreased, then mobility is decreased due to both lattice scattering and impurity scattering. Right? Yeah. Please underline the statement. Total statement. Right. And draw this plot. Mobility versus temperature graph in case of semiconductor due to both lattice scattering and impurity scattering. Right, copied. Next, note. Tell me, what is the total mobility offered by a charge carrier in a semiconductor due to both lattice scattering as well as impurity scattering? This is the equation, right? That is 1 by mu total equal to 1 by mu Ls, means mobility due to lattice scattering plus mobility due to impurity scattering. Because in case of semiconductor, two scatterings will be occur. The net mobility offered by a charge carrier is given by 1 by mu total equal to 1 by mu Ls plus 1 by mu Is. Right? For example, in a material, n scattering will be occur. N scatterings will be occur. Here two scatterings, right? If n scattering will be occur, what is the total mobility offered by a charge carrier? Here, the total mobility offered by a charge carrier, that is 1 by mu total is equal to 1 by mu 1 plus 1 by mu 2 plus so on 1 by mu n. This is okay. This is the total mobility offered by a charge carrier due to n scatterings. If two scatterings will be occur, okay, only this is the equation. If n scattering will be occur, this is the equation, right? Copy. Right. Next topic. Temperature effect on. Next topic. Temperature effect on Fermi level. in a semiconductor. Right. So now all of you, see in case of semiconductor, how the Fermi level is affected due to temperature. See here, we have two types of Fermi levels actually. One is intrinsic Fermi levels and extrinsic Fermi level. Extrinsic Fermi levels again can be classified into two, that is one is EFN, another one is EFP, because we have two types of semiconductors, right? N type as well as P type. For N type, this is for N type EFN, for P type EFP, right? First, the case one, temperature effect on EFI, intrinsic Fermi level, first of all. Before going to this temperature effect on intrinsic Fermi level actually, tell me in case of intrinsic semiconductor, where is the Fermi level lies? Right. Yeah, very good. In case of intrinsic semiconductor, the Fermi level lies exactly in the middle of the Fermi band. This is EC, this is EV, middle means EC plus EV by 2. It lies exactly in the middle of the Fermi band, right? Now, how this intrinsic Fermi level will affect due to temperature, right? Now, see all of you. See, when temperature is increased, then what happened? Thermal energy is supplied to the intrinsic semiconductor. Right? Now, thermal energy supplied to semiconductor is what? Increases. Now here, this thermal energy is acquired by the valence electrons. After acquiring sufficient thermal energy, these valence electrons can move into valency band to conduction band, and it can produce electron and hole pair. That means it can produce equal number of electrons as well as equal number of holes. It will produce equal number of electrons as well as equal number of holes means this intrinsic Fermi level remains constant, because equal number of electrons as well as equal number of holes remains constant means simply what we can say. So intrinsic Fermi level is independent of the temperature. Right, independent of the temperature. That means as temperature is increased, what about the intrinsic Fermi level? Actually, the intrinsic Fermi level lies in the middle of the Fermi band. Right, write down first the case one first. Write down the notes. The case one, temperature effect on case one, temperature effect on intrinsic Fermi level. Temperature effect on intrinsic Fermi level. Yeah. Right. As temperature is increased, then intrinsic Fermi level remains constant or independent of the temperature. That is it lies in the middle of the Fermi band. It lies in the middle of the Fermi band. Right. Copy this one. Right. Next, case 2. Case 2, temperature effect on extrinsic Fermi level. That is EFN or EFP. Case 2, temperature effect on extrinsic Fermi level. That is in bracket EFN or EFP. Right. So now, see how the extrinsic Fermi level affected due to temperature actually, right? Before going to this effect of temperature on extrinsic Fermi level, tell me in case of N-type semiconductor, where is the Fermi level? In case of N-type semiconductor, actually the Fermi level is nearer to the conduction band. This is nothing but EFN. This is the position of the Fermi level. And similarly, in case of valency band, and where is the Fermi level actually? Sorry, in case of P-type semiconductor, where is the Fermi level? The Fermi level is nearer to the valency. Nearer to the valency is nothing but this is EFP, right? This is the Fermi level for N-type, and this is the Fermi level for P-type. Now, what we are doing actually, temperature is increased. What happened, right? If temperature is increased, what about the thermal energy supplied to a semiconductor is increased, right? This thermal energy is acquired by the valence electrons, right? These thermal energy is acquired by the valence electrons, and it can produce what actually, and it can produce electron hole pair. Then what happened to EFN and EFP? You know what happened to EFN and EFP? This EFN and EFP is moving, okay, moving towards middle of the Fermi band. Middle of the Fermi band. Why? The extrinsic Fermi levels are moving towards the middle of the Fermi band as temperature is increased, because at very high temperature the extrinsic semiconductor become intrinsic. Extrinsic semiconductor become intrinsic. That's why the extrinsic Fermi level is moving towards the middle of the Fermi band. Right. And you have a doubt how extrinsic semiconductor become intrinsic because of temperature, right? That I will discuss after this concept, right? Copy first this one, case 2. Case 2, right on. Temperature effect on extrinsic Fermi level. Right on, next point. As temperature is increased, as temperature is increased, then extrinsic Fermi level is moving toward the middle of the Fermi band. Is moving toward the middle of the Fermi band, because at high temperature, extrinsic semiconductor become intrinsic. Extrinsic semiconductor become intrinsic. Right. Copy this one. Right. Next, note. Right. Here, how extrinsic semiconductor become intrinsic at very high temperature, right? Now, see this example. Here, to explain this concept, actually, here I am considering an N-type semiconductor. Tell me, N-type semiconductor, what is the condition? The condition is N greater than P. N greater than P means electrons, the number of electrons is greater than number of holes in case of N-type semiconductor, right? See, in case N-type semiconductor means, this is an example for what? Extrinsic semiconductor. You know, in extrinsic semiconductor, the conductivity is due to two types of mechanisms, right? Already I told. So one is band-to-band transition, and another one is impurity ionization, right? And another column I can consider the temperature, right? And one more column I can consider as a type of semiconductor. Now see all of you. For example, consider room temperature At room temperature means 300 degrees Kelvin, right? Uh, in this example, actually, okay, at room temperature, 100 electrons will be there, as well as 100 holes will be there because of room temperature. Actually, in n-type semiconductor, right, due to band-to-band transition, 100 electrons will be generated and 100 holes will be generated, right? And similarly, because of doping, 100 electrons will be present. Actually, very important point is this impurity ionization will depends on what? Actually, it will depends on the doping. It does not depends on temperature. But this band to band transition completely depends on what? Actually, temperature, right? Now at room temperature, actually, here 100 electrons will be there, as well as equal number of 100 holes will be there. And impurity ionization, due to impurity ionization, actually 100 electrons will be present in the sample, right? Now calculate the total number of electrons. Actually, here due to band to band transition, 100 electrons, impurity ionization because of doping, 100 electrons. That means total number of electrons are total number of electrons, that is n equal to 200 electrons, and the holes equal to 100 holes. Now clearly, what is the condition actually here? The condition is n greater than p, right? N greater than p means actually clearly what is the type of semiconductor? The type of semiconductor is n-type semiconductor. Now I am increased these temperatures to 500 degrees Kelvin, right? Now because of this increasing of temperature, what happened? These 100 electrons become 1000 electrons, and this will become 1000 holes, because equal number of electrons as well as equal number of holes now in band to band transition. That's why this is 1000 means this is also be 1000. What about impurity ionization? Because of 500 does not affect, that means 100 electrons only, right? Now what is the total number of electrons? Actually, now n equal to 1100 electrons and the holes equal to 1000 holes. Again clearly n greater than p. N greater than p means it is a n-type semiconductor, right? Now I am increasing the temperatures to 700 degrees Kelvin, right? Now this will become what? Actually 10,000 electrons. Let us say here this is 10,000 holes, and this is 100 electrons, because impurity ionization does not affect due to temperature. Now total number of electrons is n equal to 10,100 electrons, and the holes will be 10,000 holes. Again here clearly n greater than p. N greater than p means the type of semiconductor is n-type semiconductor, right? Now I am increasing these temperatures to 900 degrees Kelvin. Now this 10,000 electrons will become 1 lakh electrons, right? So this will also be 1 lakh holes, and this will be 100 electrons only in impurity ionization. And what is the n actually here? N is nothing but 1 lakh 100 electrons, and the holes will be 1 lakh, right? That means here n is 1 lakh 100 electrons and hole means 1 lakh, almost equal actually, right? That means n equal to p. N equal to p means I think what will be the semiconductor actually here? Intrinsic semiconductor. That means what is the conclusion actually here? At very high temperature, the extrinsic semiconductor become what? Actually intrinsic, because the band to band transition will dominate impurity ionization, right? Very important point. Copy this one. Right. Next, conclusion. Conclusion. At very high temperature, extrinsic semiconductor become intrinsic. Because band to band transition will dominate impurity ionization. Right? Yeah. Next topic, temperature effect on conductivity in a semiconductor. Temperature effect on conductivity in a semiconductor, right? So now, see, in a semiconductor, how the conductivity is affected due to temperature, right? So first I start with case 1. First I start with at T equal to 0 degrees Kelvin, right? See, at T equal to 0 degrees Kelvin, my semiconductor acts as a insulator, right? Okay, semiconductor acts as an insulator means what is the value of conductivity? 0. Because insulator won't conduct, so conductivity is 0. Now, case 2. Now I can increase the temperature in between 0 and 300 degrees Kelvin. Now I am increasing the temperature in between 0 and 300 degrees Kelvin actually. Now what happened? Now as temperature is increased in between 0 and 300 degrees Kelvin actually, what happened to the carrier concentration actually? The carrier concentration is increased. Carrier concentration is increased. See, carrier concentration is increases means what about the conductivity actually? The conductivity also increased, right? If conductivity increases means what about the resistivity actually? The resistivity is decreased. If resistivity is decreases means what about the resistance? The resistance also decreased, right? This is the flow graph in between 0 and 300 degrees Kelvin. Now I can increase the temperature beyond 300 degrees Kelvin. That is temperature lies between 300 degrees Kelvin and the Tc, right? Where Tc is the critical temperature. What happened in between actually? As temperature is increased, what happened? You know, as temperature is increases actually, what mobility is decreased due to collisions. If you increase the beyond the room temperature, what happened? So number of collisions is increases in a semiconductor. Because of the collisions actually, what will be the mobility actually? The mobility is decreased. Mobility of the charge carrier is decreased. If the mobility of the charge carrier is decreases means what about the conductivity also decreased? If conductivity is decreases means what about the resistivity increases? If resistivity increases means what about the resistance? Resistance also increased, right? This is in between 300 degrees Kelvin and Tc, right? Now in fourth case actually at T equal to Tc, what happened? You know, at T temperature is equal to critical temperature, what happened actually? The extrinsic semiconductor become intrinsic semiconductor. Extrinsic semiconductor become intrinsic semiconductor, right? Because band to band transition will dominate impurity ionization because of the temperature, right? Just now I discussed how the band to band transition will dominate impurity ionization, right? Now I am increased the beyond critical temperature. Beyond the critical temperature, what happened? See here, as temperature is increased, what happened actually? Okay, the intrinsic concentration is increased because now it is an intrinsic semiconductor. So as temperature is increases, actually what happened to intrinsic concentration increases. How we have a relation actually, the relation between intrinsic concentration and temperature, that is Ni square is equal to A naught into T cube e power minus Eg by kT, right? From this relation, as temperature is increased, actually intrinsic concentration is increased. If intrinsic concentration increases, means what will be the conductivity of intrinsic semiconductor increases, right? If conductivity of intrinsic semiconductor increases, means what about the resistivity? Actually the resistivity is decreased. If resistivity is increases, means what about the resistance? Actually resistance also decreased, right? So this is the temperature effect on conductivity in a semiconductor, right? Now see the complete graph, temperature, conductivity versus temperature. Actually conductivity versus temperature. First I start with 0 degrees. Actually at 0 degrees, I think temperature is 0 degrees, conductivity is 0 because it is an insulator. As temperature is increased, what about the conductivity? Actually the conductivity also increases up to what? 300 degrees, right? After 300 degrees Kelvin, actually what happened? Again the conductivity starts decreased due to collisions up to what? Actually critical temperature, right? See, at critical temperature the extrinsic semiconductor become intrinsic, right? Now you can increase the temperature beyond the critical temperature. What happened? Conductivity starts increased, right? See, this is the conductivity in intrinsic semiconductor, and this is the effect of temperature in extrinsic semiconductor, that is sigma n or sigma p, right? This is the effect of temperature on conductivity in a semiconductor, right? Copy. Yeah. See, what we can understand from this graph, actually, semiconductors offers maximum conductivity at what temperature? At room temperature, actually, from this graph, right? That means all electronic devices will be semiconductor devices are giving the best electrical characteristics at room temperature, right? And next topic, temperature effect on, next heading, temperature effect on carrier concentration in a semiconductor. Temperature effect on carrier concentration in a semiconductor. Right. So now, see here how carrier concentration is affected due to temperature in a semiconductor. Actually, in semiconductor, we have two types of carrier concentrations. Actually, one is majority carrier concentration, and another one is minority carrier concentration. Right. So here the very important thing is actually, okay, how the majority carrier concentration will affect on temperature. See here, this majority carrier concentration actually depends on what? It will depends on the doping. Actually it will depends on the doping. It does not depends on temperature. Actually it depends on what? Actually doping, right? If the doping concentration increases, then majority carrier concentration is increased, but as temperature increased, majority carrier concentration does not increased. Okay, that means it does not depend. Actually, okay, it does not depend. So simply we can say the majority carrier concentration is independent of the temperature. Coming to minority carrier concentration, actually this minority carrier concentration how affect due to temperature. See here, as temperature increases, what happen? Actually band to band transition takes place, then intrinsic concentration is increased. If intrinsic concentration increases, means what about the minority carrier concentration? Actually the minority carrier concentration is increases. Okay, here this minority carrier concentration will depends on temperature, but the majority carrier concentration is almost independent of the temperature. It depends on only what actually doping, right? Right on. Right on the points. Right on. Case 1. Case 1. Temperature effect on majority carrier concentration. Temperature effect on majority carrier concentration. Yeah, right on. As temperature is increased, then majority carrier concentration independent of the temperature. Because it depends on doping. Right. Second, case 2. Temperature effect on minority carrier concentration. Minority carrier concentration. Yeah. Right on. As temperature is increased, then minority carrier concentration is increased. Due to increase of intrinsic concentration. Right. This is how carrier concentration is affected due to temperature in a semiconductor, right? Yeah. Thank you. To be continued in next lecture.